As now we have discussed the slopes of PV diagram curve for both isothermal and adiabatic process, we are going to start with work done in isothermal process. Okay, so to calculate that work done by isothermal process, we know that isothermal process is one thermodynamic process in which temperature remains constant, right? So how we are doing it, how we are calculating is that we have taken 1 mole of an ideal gas in a container. The walls of the container, the sides of the container are perfectly isothermal or perfectly diathermal, not isothermal, perfectly diathermal. That means they are perfectly conducting. Heat can easily escape through the container or it can come inside. Okay. Now this container is fitted with a movable piston, that too frictionless. So we have taken all the ideal situations into consideration to find the work done by an isothermal process. Alright, consider that initial state of this gas is given by P1, V1 and T. What does this mean? That the initial pressure of the system is P1, initial volume of the system is V1 and initial temperature is T. Why I have not taken T1? Because the temperature T is going to remain constant because it is an isothermal. Let the gas expand. Okay, now when gas will expand, gas will perform some work on this piston, due to which it will rise up. Now what is happening? During this expansion mode, volume is increasing. So since volume is increasing, pressure is decreasing. So this is initial state. The final state would be P2, final pressure, volume V2 and temperature would still remain the same. Though pressure P2 is less than P1, volume V2 is greater than V1, we are not concerned about that, which is large, which is low. All we are calculating is what exactly is the work done. Alright. Now let's say the piston has moved. Okay, I'll come to this point, how much piston has moved and in what sense. What we are calculating is, I want to calculate work done. How can I calculate work done? Let's say F be the force which the gas is applying on the piston, so that piston is moving. So the force would be simply pressure into area. That is very true. Pressure is force upon area, so force would be pressure into area. Okay. Now consider that due to the force exerted by the gas, piston has moved to a very small distance. That means this distance covered is dx. Okay, piston has reached this point. Considering the process to be isothermal, let's say there is no change in pressure for a very small expansion. There is no change in pressure. That means P is also constant for a very small change. So therefore, small work done dW for small move in piston, that is small distance covered by the piston, would be dx. So dW would be equal to F dx, right? That means dW will be equal to, instead of F I am writing PA dx. Now what is this term? A into dx. What was A? A is the area of the gas on where force is applicable on the piston, or this complete area, right? Area from here to here is the A. So A dx is area into length. Basically it is the volume or change in volume from this to this. Total volume was V or V2, initial volume is V1, the change in volume is dV. So A dx becomes dV and dW becomes P dV, right? So if I have to calculate the complete work done from V1 to V2, I'll just integrate it. Therefore, total work done is equal to integration V1 to V2 dW. Or instead of dW, I'll write V1 to V2, this becomes P dV. Now, I can take P here. We know according to ideal gas equation, we have PV is equal to nRT. N is the number of moles. We have taken 1 mole of gas, right, in this ideal situation. So N becomes 1. I am left with just R and T. Both are constants because in this case temperature is not changing, so T is also constant. So from here I'll get P is equal to RT over V, right? Put this value of P in this equation. I'll get, instead of P I am having RT over V dV from V1 to V2. Alright. Now I can delete that. So moving on further, total work done, R and T are constants, they come out of the integration. I am left with integration V1 to V2 dV upon V. What is 1 upon x? Integration 1 upon x ds, log x. So this will become log V RT log V from V1 to V2. One very important thing, that from integration the log which you get is the natural log, that is the exponent is the base. To convert this into base 10 thing, we multiply the whole thing with what? 2.303, right? Okay, we'll do it later. But first, putting the limits, that is upper limit minus lower limit, I'll get RT log V2 minus log V1. Okay, log A minus log B is log A upon B. RT log A upon B, which is V2 over V1. E. And now this is the final answer, but only one step is required, which is the base exponent has to be converted into base 10. So this equation becomes 2.303 times RT log V2 over V1. This is the value or the equation of work done in an isothermal process where volume increases from V1 to V2. Now, if I want to write this equation in terms of pressure, use this. We know that PV is equal to constant. That was the equation in isothermal process. So PV is equal to constant. This means P1 V1 will be equal to P2 V2. I want V2 upon V1. This. So P1 over P2 will be equal to V2 upon V1. So instead of V2 upon V1, here I can write this whole equation in terms of pressure. So this will also be equal to 2.303 times RT log, instead of V2 upon V1, I am writing P1 upon P2. So this is my answer for work done in an isothermal process.